In this unit, we're going to discuss radicals and simplifying radicals. We're going to discuss the rules of exponents, or review the rules of exponents. And then we'll deal with solving some radical equations as well. So let's first start with a review of our rules of exponents. So in this case, we're going to simplify the expression 3a squared b over 2b to the negative fourth power, all raised to the third. So the first thing that we're going to do is we're going to incorporate the power rule. And just for review, the power rule states that when we raise a power to a power, so let's say we had x raised to the a power, all raised to the b power. Anytime we raise a power to a power, we multiply the exponent. So this would be x to the ab power. Okay, the other rule that we may incorporate would be the negative exponent rule. And the negative exponent rule states that whenever we raise a base to a negative power, that we take the reciprocal of the base. So what we're going to do is take this a to the negative fourth and take the reciprocal of our base a, which becomes 1 over a to the positive fourth. So all that the negative does as far as the exponent rule is tells us to take the reciprocal of our answer or of this base. So notice it changed from a negative exponent to a positive exponent when it was moved into the denominator and after we took the reciprocal. So these are reviews of things that you should know coming into this class, and I'll do that as we progress through this unit. So the first thing I'm going to do is use the power rule. But before I do that, what I want to do is restate this as 3 to the first, a to the second, b to the first, over 2 to the first, b to the negative fourth, and again, all raised to the third power. I do that to remind me and you that every single factor has an understood exponent of 1 if it's not shown. Because when we're using this power rule, we're going to multiply the exponents. So this becomes 3 to the third power by multiplying the exponent 1 times the exponent 3. Then a to the sixth, b to the third, over 2 to the third, b to the negative 12th. So what we're going to do next is deal with the negative exponent rule. So again, when we are using the negative exponent rule, it says we take the reciprocal. So all that's going to do is move the b to the negative 12th power up to the top, and we'll change the sign of the exponent, because what we're doing is taking the reciprocal, so the denominator becomes the numerator. So what we'd have here is 3 to the third, which is 27, a to the sixth, b to the third. Now we have b to the 12th joining the b to the third, because remember, b had a negative exponent in the denominator, so it moves up to the numerator. And we have 2 to the third, which is 8 in our denominator. The next rule we're going to use is the product rule. And again, for review, the product rule states that whenever we multiply like bases, so x being the base in this case, when we multiply like bases, we add the exponents. So in our numerator, we have 27, a to the sixth, b to the 15th now, because we're adding the 3 and the 12 together, and that's all over 8. So let's look on to the next example. So again, the first thing that I'm going to do is rewrite it so that everything is shown with an exponent. So that's 2 to the first, x to the first, y to the negative first, over y to the fourth, all raised to the negative third power. So my next step is to multiply the exponents. So this becomes 2 to the negative third, x to the negative third, y to the positive third, because I'm multiplying -1 times -3, all over y to the -12th. Next, let's use our negative exponent rule. So if it has a negative exponent associated with a factor, we take the reciprocal, which will move anything that has a negative exponent in the numerator to the denominator, and anything with a negative exponent in the denominator to the numerator. So let's look and see what happens. So the 2 is raised to the -3rd power. So now that moves down to the denominator as 2 to the +3rd. The x to the -3rd does the same. So it becomes x to the 3rd in the denominator. The y in the numerator has a positive exponent, so it remains in the numerator, no change. And we have y to the -12th in the denominator, so that moves the factor to the numerator. Our next step will be to simplify. So we're going to use the product rule. So we have y to the 3rd times y to the 12th. So we add, and that becomes y to the 15th. In the denominator, we have 2 cubed, which are 8, because 2 times 2 is 4, times 2 is 8, and x to the 3rd. So our final answer is y to the 15th over 8x to the 3rd. Now let's look at the quotient rule. So the quotient rule states that whenever we're dividing like bases, so if we have a to the x over a to the y, we subtract the exponent. So it's a to the x minus y. So in this case, we have x to the 7th over x to the 1/8 power. So we're going to use the quotient rule. So we're going to have x to the 7th minus 1/8. Now we have to get a common denominator. So what we have is 7 over 1 minus 1/8. The common denominator is 8. So we need to multiply numerator and denominator of the 7 by 8. So 7 times 8 is 56. Over 1 times 8 is 8. And now we subtract. 56 minus 1 is 55. So our answer would be x raised to the 55 over 8. Okay, next, notice we're multiplying like bases. So when we multiply like bases, the base remains the same, and we add the exponent. So we'd have y to the 6 over 11 plus -1 over 22. In order to combine, we need to get a common denominator, and our common denominator would be 22. So we need to multiply numerator and denominator by 2 with the 6 over 11 so we can get a common denominator, and that gives us 12 over 22. Now we add 12 over 22 plus -1 over 22, and that gives us 11 over 22, which can be reduced to 1/2. So the answer to this would be y raised to the 1/2 power. Our next example, we're evaluating 25 raised to the 3/2 power. So we're going to use the power rule here. But before we do that, what we want to do is break our base down into prime factorization. We're going to use prime factorization a lot in this unit. So what we're going to do is take 25 and use that factoring tree and break 25 down into a product of primes. So 25 is 5 squared. So we're going to rewrite 25 as 5 squared raised to the 3/2 power. So again, when we raise a power to a power, we multiply the exponents. So we have 5 squared, or I'm going to make it 2 over 1, times the 3/2 power. I can reduce 2 goes into 2 one time and multiply straight across. So this would give me 5 to the 3 over 1 power, which is 5 to the third, because I'm multiplying numerator times numerator, denominator times denominator. And now I simplify. 5 to the third power is 5 times 5 times 5, which is 125. My next problem, I'm going to do the exact same thing. So we're going to start by breaking 243 down into prime factorization. So we're going to start, since it's an odd number, we're going to start by trying 3. So we're going to take 243, and we'll put the negative sign in front at the end, is 3 times 81. 81 can be broken down again by 3 times 27. 27 can be broken down to 3 times 9, and 9 can be broken down into 3 times 3. So we have 2, 3, 4, 5 factors of 3. So this is 3 to the 5th power. Okay. So now we have a power raised to a power. So what we're going to do is multiply our exponents. So we'd have negative 3, and we have 5 over 1 times 4 over 5. 5 goes into 5 one time. So this would leave us negative 3 raised to the 4th power. And negative 3 to the 4th power. Anytime you raise a negative number to an even power, your answer is going to be positive. So this is going to be negative 3 times negative 3, which is positive 9, times negative 3, which is negative 27. And negative 27 times negative 3 is positive 81. So we're going to break it down into prime factorization first, and then we're going to use the power rule. Now let's discuss breaking down radicals and simplifying. There's a variety of ways to do this, and I'm going to show you a couple of techniques. Let's start by looking at what we call perfect squares. So I've written 1, 4, 9, 16, etc. How did I get those numbers? 1 is 1 times 1. 4 is 2 times 2. 9 is 3 times 3, etc. So when we look at the square root of a number, so the square root, we use the radical sign. So when we're asked to find the square root of a number, what's being asked is, what is multiplied times itself that would give you the answer A? So if I had something like the square root of 4, the square root of 4 is 2, because 2 times 2 gives me 4. And that's what I've written with the 1, 4, 9, 16, etc. Those are all what we call perfect squares. So when I look at the square root of 100 as my first example, what multiplied times itself gives you 100? And the answer is 10. So now when we look at our next example, it's the square root of 12. Well, there's no whole number or integer multiplied times itself that gives you a 12. Some of you may be thinking 6. 6 times 6 gives you 36 and not 12. So what we have to do is break this down. So here's the first technique. Whenever you're dealing with square roots, what you want to do is use one of the perfect squares as a factor. So what we're looking for is the highest perfect square factor that divides into 12. So what I do is I would start at 9, and 9 doesn't go into 12, so I work my way down. So I choose the one closest to what's called my radicand. The radicand is the number underneath the radical sign. So I look at the highest value closest to 12 without going over, and that would be 9. 9 doesn't go into 12, so I can't use 9, but 4 does. So in simplifying, I rewrite 12 as the highest perfect square factor times whatever value is necessary to give me the 12. So we know 4 times 3 is 12. I use 4 because 4 is a perfect square. I wouldn't have used 6 and 2 because neither 6 nor 2 is a perfect square. So now I simplify. The square root of 4, what multiplied times itself gives you 4, and that would be 2. And so since 3 isn't a perfect square, it remains underneath the radical sign. So the answer to the square root of 12 is 2 times the square root of 3. Now let's look at another example, the square root of 75. So what I do, since 75 isn't a perfect square, I come to the closest perfect square factor of 75, and that would be 64. 64 doesn't divide into 75 evenly, so I'm going to work my way to the left to find one that will. If none do, then it's simplified as the square root of 75. So 64 doesn't go into 75, nor does 49, nor does 36, but 25 does. So I'm going to rewrite 75 as the square root of 25, because 25 is a perfect square factor, and 25 times 3 gives me 75. Notice they're both underneath the radical sign. 25 is a perfect square, so you ask yourself what multiplied times itself gives you 25, and that would be 5. So our answer would be 5 square roots of 3. Our next example is 3 square roots of 32. So what I'm going to do is look at my perfect square factors. I'm going to find the highest perfect square factor that goes into 32. So I start with 25 because that's closest and work my way down. So 25 doesn't go into 32, but 16 does. If you don't use this approach, this can get you in trouble because there's actually 2 perfect squares that divide evenly into 32, 16 and 4. So if you chose 4, then you wouldn't have broken down the radical into its simplest form. So 16 goes into 32. So what do we do with this 3? So we just keep the 3 in front. So it's 3 times the square root of 16. And 16 times some number gives me 32. And of course, that's 2. So my next step is to simplify the perfect square. So I still have the 3 on the outside. So it's 3 times the square root of 16 is 4, because 4 times 4 gives me 16, and I still have my square root of 2. 3 times 4 is 12, so my final answer would be 12 square roots of 2. Okay, now I want to introduce something different. Now this helps whenever we're dealing with variables. So whenever we're looking at radical signs, so when we're looking at square root, we're going to also be dealing with what we call cube root, maybe fourth root, fifth root, etc. So this number that's up top of the radical is called the index. So the index tells you how many times a number needs to be multiplied times itself to give you the radicand. Okay, so when I look at the cube root of 8, for instance, I'm not saying what multiplied times itself gives me 8. What number multiplied times itself 3 times gives me 8, and that would be 2. And we'll talk about simplifying in a moment. So all of these have indexes shown: cube root, fourth root, fifth root, but square root doesn't. It has an understood index of 2, but it's never shown. Similar to whenever we look at a variable when it's an x, there's a 1 understood in front, but it's never shown. Same thing with square root. So square root means what number multiplied times itself, and again, our index would be 2. So what I'm going to introduce is another process of simplifying, and I use what's called a division of exponents. So what I'm going to do is I'm going to show you this particular problem. I'm going to rewrite it, but I'm going to write the index 2. So that's a to the 7th, b to the 12th, and c to the 15th. So what I do to simplify is I divide the exponent by the index. So for the a, I'm dividing 7 by 2. So 2 goes into 7 3 times with a remainder of 1. Okay, so the number of times that it goes into a specific value is the exponent on the outside of the radical sign. So this becomes a to the 3rd. The 3 again is the number of times that, in this case, 2 went into 7. Now you say, well, what do you do with the remainder? The remainder is the exponent of that factor underneath the radical sign. So when you have a remainder, it remains underneath the radical sign. So let's look at b to the 12th. So I have 12 divided by 2 is 6. So that means 6 are on the outside, and 2 goes into 12 with a remainder of 0. So 0 b's remain underneath the radical sign. Let's look at the next one, c. So we have 15 divided by 2. So 2 goes into 15 7 times with a remainder of 1. So that means we have 7 factors of c on the outside. Since we have a remainder, 1c remains underneath the radical sign. So when we're showing our answer, we don't show the exponent of 1. So our answer would be a to the 3rd, b to the 6th, c to the 7th, times the square root of ac. We're going to be using this approach more, so you'll see more examples coming up. Okay, so the next example is the square root of -9. So the square root of -9, so remember, it's asking us what number multiplied times itself equals -9. Well, there's no real number, because if I multiply a positive times a positive, my answer is positive. You say, well, what about negative? Well, if I multiply a negative times a negative, I also get a positive, because remember, we're saying what number multiplied times itself equals this number. So if you multiply a number times itself, a positive times a positive or a negative times a negative, you'll never get a negative. So there's no solution under the set of real numbers. Okay, so now let's go through this technique we just talked about a minute ago with the division of exponents. So here we have the cube root. So the index here is 3 of x to the 8th, y to the 12th, z to the 16th. So I'm going to rewrite that. So again, it's the cube root of x to the 8th, y to the 12th, z to the 16th. So we're going to go ahead and simplify. So we're going to start, and you can do this in your head if you want. I just want to show you. So we start with the exponent 8, and on the outside is our index. In this case, the index is 3. So 3 goes into 8 2 times with a remainder of 2. So that means I can take out 2 factors of x, but I had a remainder, so that means 2 still remain underneath the radical sign. Important that you put the index back in as part of your answer. So the next one, I'm going to look at my y. So I'm going to have 12, which is my exponent of y, divided by my index. So 3 goes into 12 4 times with a remainder of 0. So that means I can take out 4 factors of y and 0 remain underneath. So the last is the z. So it's z to the 16th. So I put my exponent, which is 16, with my index, which is 3 in this case. So 3 goes into 16 5 times. So 5 times 3 is 15. That means we have a remainder of 1. So that means I can take out 5 factors and I have 1 that remains underneath. And again, I don't show this exponent as a part of my answer, but it's understood. Okay, so next, we have the fourth root of 32, a to the 10th, b to the 15th. So we don't divide 4 into 32. Remember, we're just dividing exponents. So what do I need to do to express 32 so it has exponents? I'm going to use the factoring tree. So I'm going to start out with whatever my coefficient is. In this case, it's 32. Since 32 is an even number, I know that 2 will go into it. And I keep breaking down the number. So 32 is 2 to the 5th power. So when I'm rewriting my expression, this becomes the fourth root of 2 to the 5th, because that's what 32 is, a to the 10th, b to the 15th. So now I do my division of exponents. So 2 is raised to the 5th power, so I divide that by my index. And again, my index in this case is 4. So 4 goes into 5 one time with a remainder of 1. So that means I can take out one factor of 2 and 1 remains because of my remainder. Notice again, I put my index 4 back in as a part of my answer. Now I'm going to break down a to the 10th. So I put my exponent 10 divided by my index. Since we're dealing with fourth root, it's 4. So 4 goes into 10 2 times with a remainder of 2. So that means I can take out 2 factors of a, and my remainder was 2, so 2 remain underneath the radical sign. Last, I do my b, that's b to the 15th divided by 4. So 4 goes into 15 3 times with a remainder of 3. So it would be b to the 3rd with b to the 3rd underneath. So my final answer is 2a squared, b cubed, or b to the 3rd power, times the fourth root of 2a squared, b to the 3rd. Another example. Here I have the cube root of 108, x to the 9th, y to the 22nd. So remember, we're not dividing 3 into 108. We need to break 108 down into prime factorization. So we're going to start with 108. Since it's an even number, we know 2 will go into it. We know 2 will go into 54. Now, since 27 isn't even, we're going to go to 3. So 108 is 2 to the 2nd and 3 to the 3rd. So we're going to write that as 2 separate factors, 2 to the 2nd, 3 to the 3rd, x to the 9th, y to the 22nd. So now we're going to break it down. So we're going to start with 2. So we have 2 squared. So our exponent is here, divided by 3. So 3 goes into 2 0 times with a remainder of 2. So that means we can't take out any 2's. So the 2 has to stay underneath. So again, I write in my index, and this is 2 squared. Next, I'm going to go to 3 to the 3rd power. So my exponent is 3. My index is 3, and 3 goes into 3 one time with a remainder of 0. So I can take out one factor of 3. Next is x to the 9th. So I'm going to take my exponent 9, divide it by my index, which is 3, and 3 goes into 9 3 times with a remainder of 0. So that means I can take out 3 factors of x with a remainder of 0, so no x's remain underneath the radical sign. And now my y's. The exponent is 22. My index is 3. 3 goes into 22 7 times with a remainder of 1. So I can take out 7 factors of y with 1 remaining underneath. So now on the outside, I have 3 x to the third, y to the 7th. Remember, you're going to write in your index, so it's the cube root. We know 2 to the 2nd power. 2 times 2 is 4 times the y. The next, we're going to take square root this time. So again, when I'm simplifying, that -3 stays on the outside. Remember, square root has an index of 2, so I'm going to write it there. 72 we need to break down into prime factorization. Again, since it's an even number, I start with 2. So 72 is 2 to the third times 3 squared. So it's 2 to the third times 3 squared. I still have my a to the 5th and b to the 13th. So now I'm going to divide my exponents. So this -3 still is on the outside, and I have my square root just in case I have remainders, but I'm not going to write the index because it's understood. With square root, you never write the index as a part of your final answer. Okay, so now I do my division of exponents. So I'm going to do it without writing it this time. So I divide 2 into 3. 2 goes into 3 one time with a remainder of 1. So now I go to my 3 squared. So 2 goes into 2 one time, but it went in evenly, so there's no 3's that remain. Next, my exponent of 5. 2 goes into 5 two times with a remainder of 1. And then for my 13, 2 goes into 13 6 times with a remainder of 1. So on the outside, I'm just going to multiply what I have. -3 times 2 to the first. So -3 times 2 is -6 times 3 to the first. So -6 times 3 is -18. A to the second, b to the 6th times the square root of 2ab. So this technique works no matter what your index is. That's why I like it so much. So the first problems that we did where we found the highest perfect square factor, if that's confusing to you, with practice, this is the best way to do it, or maybe the best way. You need to understand both, but whatever you use, make sure you feel comfortable and practice.